In this video, we're going to be discussing how to find intercepts, how to identify the symmetry of a graph using the equation, and a little bit on circles. An x-intercept of a graph is where your graph intersects the x-axis. So if I have a graph like this, where does my graph intersect the x-axis? Here's my x-axis, it intersects here and here. So the ordered pairs would be -2, 0, and 2, 0. So those would be my x-intercepts. For my y-intercepts, that's where my graph intersects the y-axis. So here's your y-axis. Your graph intersects it right here. So what's the ordered pair of that point? 0, -2. So this graph would have 2 x-intercepts and 1 y-intercept. If you look at these ordered pairs, you notice this common kind of theme with the 0. To find an x-intercept, the y is going to always equal 0, right? No matter where you are, this is -4, 0. No matter where you are on the x-axis, the y-coordinate will always equal 0. So to be able to find an x-intercept, what you can do is you can set y equal to 0 and solve for x. So if you're not given the graph, you can use the equation to help you find the intercepts. A very similar pattern exists with the y-intercepts as well. If you look at this value, you get 0, -2. Well, if my graph intersected up here, that would be at 0, 3. If it intersected down here, it's 0, -1. Or down here, it would be 0, -4. So you can see that the x-coordinate will always equal 0. So even if you're not given the graph, you can still find the y-intercept by setting the x equal to 0 and solving for your y values. How many x-intercepts would a graph like this have? It looks like it would have 1 x-intercept. How many y-intercepts would a graph like this have? 2 y-intercepts. How many x-intercepts would this graph have? How many y-intercepts? Well, it actually never hits the x-axis, so it would have no x-intercepts. And it would never hit the y-axis, so it would have no y-intercepts. So you can have a big range of answers here. If I have a graph that looks like this, and it keeps going with that pattern, keeps curving down, I notice that it has infinitely many x-intercepts and only 1 y-intercept. If I have a line, let's say the vertical line right through the origin, it would only have 1 x-intercept, and that would be right here at the origin. And it would have infinitely many y-intercepts. It would hit here and here and here and here and here and everywhere along that equation right there. Everywhere along that line. Okay, finding the intercepts when you're given the equation. To find the x-intercepts, remember you substitute in 0 for y. So we're going to get 0 equals the opposite of x minus 2, the absolute value of that. To solve an absolute value equation, you first need to isolate it. So I have to divide both sides by -1. 0 divided by -1 is just 0. Now typically from here I set up my two equations, x minus 2 equals +0, x minus 2 equals -0, but you can see that when an absolute value is set equal to 0, you're going to get that same answer twice, so you don't even really have to set up the two equations. So you're going to get x equals 2. Now how do you write your x-intercept? You write it as an ordered pair if your final answer is an ordered pair, which it is in this case. 2, 0. The x-coordinate equals 2, while the y-coordinate equals 0. To find the y-intercept, you're going to substitute in 0 wherever you see an x and solve. So you're going to get y equals negative, the absolute value of 0 minus 2. So to use rule of operations, we have to simplify inside here first. So we get -2. Bring everything down. Solving this piece first, I get the absolute value of -2. The absolute value of -2 is +2. But there's kind of like a -1 attached here by multiplication. It's really the opposite of whatever I get there. So I got 2. So now I need to take the opposite of that. So the opposite of 2 is negative 2. So when my x is equal to 0, my y is equal to negative 2. So these would be my two final answers for part 1. For this problem, I'm going to find the x-intercept by setting y equal to 0 and solving. So I get 0 equals, see how we're bringing some old skills that we already reviewed into play. So now, again, I have to isolate the absolute value bars. So I'm going to add 6 to both sides. Then I'm going to divide both sides by negative 3. And then usually I make my two equations here, but the absolute value is equal to a negative number. That's never going to happen. No matter what x value I substitute into this equation, I'm never going to get a negative answer out, right? The absolute value, the smallest this quantity can ever be, is 0. It's never going to be a negative number. So there's actually no solution to that equation, which means that there are no x-intercepts. And I would just write the word none. For the y-intercept, I'm going to substitute in a 0 wherever I see an x. Simplify inside here first. Bring down this negative 3 times the absolute value of 3 minus 6. So the absolute value of 3 is 3. Multiply that by negative 3. Subtract 6 from that. So negative 9 minus 6 equals negative 15. So I get 0, negative 15 for my y-intercept. We'll try 2 more examples. To find the x-intercept, I'm going to substitute in 0 wherever I see a y. So I get x equals negative 2 minus 0 squared. 0 squared is just 0. So you get x equals negative 2. So your x-intercept is negative 2 comma 0. For your y-intercept, you're going to substitute in a 0 wherever you see an x. So we're going to get 0 equals negative 2 minus y squared. So we're going to add, I like to add y squared to both sides here. And I get y squared equals negative 2. So I'm going to take the square root of both sides. Oh, that's a negative. I'm taking the square root of a negative. That's not a real number. So since I get no solution from that equation, there's actually going to be no y-intercept. So I would just write the word none. For this problem here, to find the x-intercept, I'm going to substitute in a 0 wherever I see a y. So when I substitute in 0 here, I just get x equals 1. So this becomes 1 comma 0. When I substitute in a 0 for x, I'm looking for the y-intercept. So substituting a 0 for x, I'm left with this. So now I'm going to add 2y squared to both sides. And I'm going to isolate my quantity being squared, so I'm going to divide both sides by 2. Then I'm going to take the square root of each side. When I take a square root, I'm going to get plus or minus. The square root of 1 is 1 over the square root of 2. I don't know, so I leave it. Now I have to rationalize this, so I need to multiply by 1, which in a different form I'm going to choose the square root of 2 over the square root of 2. So I'm going to get plus or minus square root of 2 over square root of 2 times square root of 2 equals 2. Or you can think of it as the square root of 4, which then equals 2. So this will be 2 solutions. So I'll have 0, negative root 2 over 2, and 0, positive root 2 over 2. I have 2 solutions here. When I list them in roster form, I separate them with a comma, and I use my curly braces on the outside. That's just representing a set with more than one element. When you're thinking about symmetries for the x-axis, what that means is if you can reflect the upper part of your graph over the x-axis and have the same corresponding ordered pairs on each side, it will be symmetric with respect to the x-axis. Now, if I have a point, let's call this AB on my graph, I also have to have the point A, comma, negative B. See how the x value stayed the same, but the y value just became the opposite sign? That's for symmetric with respect to the x-axis. To test to see if something is symmetric with respect to the x-axis, you're going to replace the y with a negative y. If you get the original equation out, it will be symmetric with respect to the x-axis. If something is symmetric with respect to the y-axis, it can look something like this. For every point AB on your graph, you'd have this point over here. See how it's symmetric with respect to the y-axis? It's on the opposite side of the y-axis, so this is going to be the opposite sign of A. But you see that it's going to be the same exact y value. So you have the point negative AB on your graph as well. And this should be true for all points. Now to test this, what you have to do is replace the x with the opposite of x. So to test for y-axis symmetry, replace the x with negative x. If you get out the original equation, it will be symmetric to the y-axis. If something is symmetric with respect to the origin, it's going to have rotational symmetry of 180 degrees, and the point will be the origin. If I have an ordered pair, A, B, right, so if I take my paper and I rotate it 180 degrees around this point, do you see that I end up with this portion down here? So for each point A, B on my graph, I also have this corresponding point down here. The A value didn't change much except for it's on the opposite side. So we represent that with a negative A. The B value didn't change except it's on the opposite side. So it's going to be negative B. So for each point A, B that lies on the graph, you should also have a corresponding point negative A, negative B on the same graph. To test for origin symmetry, you have to replace the x with negative x and the y with negative y. If you get out the original equation, it will be symmetric with respect to the origin. To check for x-axis symmetry, what you want to do is you want to replace your y with the opposite of y and leave everything else the same. Does this equal the original equation? Here's your original equation. Well, no way. But if you're unsure, you can divide both sides by a negative 1. If you divide this binomial by negative 1, you have to do it to each term. This does not equal the original equation. Okay, so what that means is it is not symmetric with respect to the x-axis. Now we want to see if it's symmetric with respect to the y-axis. So I'm going to substitute in a negative x wherever I see an x. Make sure you substitute that negative x in parentheses when needed. So just a quick tip here. Negative x quantity squared is just negative x times negative x, which is just x squared. Another tip you can have is if I had something cubed, negative x cubed, that's just negative x times negative x, which is positive x squared, times a negative x again. So that's going to be a negative x cubed, so you can actually take that negative sign out. For this case, when it's squared or to an even exponent, this will work for every even exponent. This will work for every odd exponent. So when it's even, you see that you can kind of lose the sign in front. When it's odd, you keep whatever sign of the entire x quantity. You can rewrite the absolute value of negative x as the absolute value of regular x as well. These two are equivalent. Remember, x can be any quantity. Okay, so now that we remember those properties, we get y equals 2 plus, this becomes negative x times negative x, which is really just x squared. This is actually equivalent to the original equation, so it should have symmetry with respect to the y-axis. Now we need to check for origin symmetry. To check for origin symmetry, we replace the y with the negative y, and we replace the x with negative x. So this stays the same. Negative y equals 2 plus this becomes x squared. This is kind of reminding me of when we checked for x-axis symmetry at this point. So if I want to double check, I can say divide by negative 1, divide by negative 1, divide by negative 1. This does not equal the original equation, so that is out. You kind of have 5 options for symmetry. It can be symmetric with respect to the x-axis, or just the y-axis, or just the origin. Or it could be symmetric to all 3, or it could have no symmetry. Your final answer for this problem is it's just symmetric with respect to the y-axis. To check for symmetry for this problem, I'm going to substitute in a negative y wherever I see a y. the absolute value of y is just equal, the absolute value of negative y is just equal to the absolute value of y. This is actually the original equation. So it works. So it's symmetric with respect to the x-axis. Now we need to check for y. Is it symmetric with respect to the y-axis? Well, if I substitute in a negative x and it yields the original equation, then yes. So let's see. This stays the same, equals, this becomes just x squared. Bring down the plus 3. This is the same as the original equation, so it also has y-axis symmetry, which means it should probably have origin symmetry, but we need to substitute these values in to make sure. The absolute value of negative y, right, we replace our y with negative y, and our x with negative x. The absolute value of negative y is just the absolute value of y, is equal to negative x squared is just x squared. The plus 3 stays the same. So this is actually the original equation. So it's symmetric with respect to the x-axis, to the y-axis, and the origin. To check for x-axis symmetry, I'm going to replace the y with negative y. And I'm going to get y equals, divide both sides by negative 1. Change sign, change sign. This is not equal to the original, so it does not have x-axis symmetry. Does it have y-axis symmetry? Well, I replace my x with negative x and see if it yields the original equation. Negative x times negative x times negative x equals negative x cubed minus 1. This is not the original equation, so it's not symmetric with respect to the y-axis. Now I need to check for symmetric with respect to the origin. Negative y equals negative x cubed minus 1. So I get negative y equals negative x cubed minus 1. Divide both sides by negative 1. And this does not yield the original equation. So close, but that sign is off right there. So this actually has no symmetry. I'm going to review a few of the concepts that we talked about today. So when I'm looking for the x-intercepts, what I'm looking for is to figure out if my graph will intersect the x-axis. So what is always true about points on the x-axis? The y-coordinate always equals 0. So that's how I find the x-intercept. I substitute 0 in for y. So this becomes just x squared equals 25. So I get x equals plus or minus 5. So I have two x-intercepts, 5, 0, and negative 5, 0. And I can go ahead and plot them. To find my y-intercepts, I'm going to substitute in 0 wherever I see an x, and I'm left with y squared equals 25, and y equals plus or minus 5. Okay, now I need to test for any symmetry. To test for x-axis symmetry, I replace my y with negative y. Does it yield the same equation? Yeah, this just simplifies to the original. So it does have x-axis symmetry. Does it have y-axis symmetry? I replace my x with negative x. Right, do you guys see that that would just become x squared? Everything else stays the same, which means it matches the original equation. So it does have y-axis symmetry as well. Now I need to know, does it have origin symmetry? If I replace the x with negative x and the y with negative y, do I get the original equation? Negative x quantity squared is just x squared. Negative y quantity squared is just y squared. Since it yields the original equation, I actually have symmetry with respect to the x, the y, and the origin. And now I need to find a few additional points. So substituting in a 0 would have been a good idea, but I already had two output values. So substituting in a 1 would be a good idea. If I substitute in a 1 for x, let's say, I get 1 squared plus y squared equals 25. So if I subtract 1 from both sides, right, 1 squared is 1, so I subtract 1 from both sides, I'm left with an irrational number. You can graph irrational numbers approximately, but maybe let's try to find a nicer value. So if I tried to substitute in a 2, I'd be subtracting 4. Square root of 21 is still irrational, so maybe I could try 3. If I substitute in a 3, wherever I see an x, I get 3 squared, which is 9, plus y squared equals 25. So I get y squared equals 16, so y equals 4, and y equals negative 4. And the nice thing about this is I can use my symmetry to reflect those points, right? It should be symmetric with respect to the y-axis. So I should be able to reflect these points over. It was 3 away, so it should be 3 away on this side as well. Same thing on the bottom. It should be 3 away. Now it's 3 away over here. All right, so if substituting in 3 works, I think substituting in 4 should also work. 4 squared is 16. If I subtract 16 from both sides, I get y squared equals 9. So y would equal 3 or negative 3. So when x equals 4, y equals 3 or negative 3. So I get out 2 points right there. And I can just reflect them over. Do you see that we're getting closer and closer to a circle? Where is the center of my circle? It's right here at 0, 0. Notice how 0, 0 is not actually on the circle. So if I substitute in 0, 0, it's not a true result. That's because the center is not actually a point on your circle. What a circle is, it's the point of all values that are equal distance away from a fixed point. So that fixed point is called your center. That fixed distance is called your radius. So no matter where you are on this circle, let's say you're here, this distance from here to here should be 5.